Well, hello and welcome to another episode of Undercooled. Today we're going to talk to Tim about what he does in his undergraduate lab that he teaches and how he teaches alloy design to undergrads, to juniors who are just taking thermo for the first time while they're in the course. And he's going to tell us how he has them use ThermoCal and COMSOL and other things to design the alloy on the computer, make the alloy, and then measure mechanical properties to see if they get the mechanical properties they were designing the alloy to attain. So this is really exciting to me. And so welcome, Tim, and maybe you can tell us how you do alloy design in a first-time undergraduate materials lab.
Yeah, that was such a good summary of the semester. I feel like my work here is done. So everyone tune in next time for another episode. There's a couple of challenges in this course that are part of the course design. But as always, it starts with the learning objectives. What do I want students to take away from this course? And I identified a big three that I wanted to focus on. The first was it being a lab course. I do want students to learn about lab equipment and MSE, what are the canonical tools that we use, and how do they perform materials characterization experimentally. But in addition to that, it's also very important to have some foundation in theoretical methods in using simulation and using computational tools to understand materials and materials properties as well. So one of my big goals for the course was that students would end up in a place where they could combine theoretical models with their experimental data to ask good why questions about why is the material behaving this way and to attempt to answer those questions. Then the last one was something that I really heard from students over the years as I've been developing this course, that they wanted to be more prepared for their senior design courses. And so I said, well, if this is a junior lab, what can I do with the juniors to give them an authentic design experience so that when they get to senior design, they're not doing it for the first time and they feel prepared. So those were the goals for the course design.
Well, that's great. And I think it's really important to also note that for many of these students, this is the first time they've ever walked into a laboratory. So when do you actually start the alloy design? It's probably not your first project in the term.
No, it's the third project. It's the final project for this semester. And you're completely right. For all of our students, it's their first MSE lab. For many of our students, it's the only lab that they've taken since maybe their Physics 1 or Chemistry 1 lab freshman year. And rolling blocks down slopes or balls or whatever it is they do these days in physics, is not exactly the same as doing tensile testing and pouring metal and doing finite element analysis. So there's this huge gap in terms of what the students are prepared for when they come to this course. Now, looking at what they do know coming in, understanding their sort of beginning knowledge state, is they've taken the introductory MSE course, and that's it. So on the one hand, I know what students do know, but I also have to coordinate with the other courses that they're taking at the same time, because there's no way I could teach all these things in one semester. And so I'm talking to the faculty teaching our thermodynamics course and our structures course, which are over 90% of the students take the lab and thermo and structures at the same time. So I'm working with these faculty to say, hey, what are you doing 3 weeks from now in thermodynamics? What can I do to prepare students for that course so they can go to your class and revisit that topic and reinforce it and then come back to the lab more prepared than before? So that's a lot of what is happening in the first half of the semester. We're doing projects. I'm teaching tools and techniques, data analysis, experimental design, a lot of fundamentals, and coordinating with the other classes to get students ready for the big deal, the actual project where they really design and make something.
Right. And of course, all of this while students are still learning that most of the time when you set out to do an experiment in the lab, it doesn't come out the way they expect it to come out, like it does in all those contrived physics and chemistry experiments where 90% of the students get the right answer. But we know in reality, in real research, you rarely get the answer. And it's all about learning how to embrace failure. And failure is a good thing, because if you don't know what the outcome is going to be, chances are you're not going to get the outcome you predict. But that is an opportunity to figure out why.
Absolutely.
And after you figure out why, of course, then you can go back and refine your model and start to get some repeatability. So and I know that you do that in the class, because I've seen a lot of the modules, and, things don't always work out. And that's probably the most important part of that early times in that class.
Yeah, the first project in the course is something that requires the students to bring in a consumer product, a real good from the actual world that was made by real engineers and sold to real people. And they bring that into the lab and do characterization and do analysis on it, because often the answers are complicated, messy, sometimes wrong. Sometimes a product is labeled as material A and it's actually made out of something else. And it's exactly as you said, to give students that experience of things often don't work, or at least don't turn out the way you expected. But in this case, by letting the students bring in someone else's work that they can find out it's quote unquote wrong, it takes some of the pressure off the students. So they're not in this space of, oh, I screwed up, I'm a bad scientist, I guess I'll just quit. They realize, no, sometimes things in the real world are just not what they claim to be, or not what they're supposed to be. And that's part of what we have to deal with as we're doing our jobs.
Yeah, that reminds me of a funny story. I was involved on a DARPA project with quasi-crystals. They even had Dan Schechtman there on the project. And Laurie Marks from Northwestern, who's a really great scientist. He had this whole thing was based on helping the warfighter not have to carry as much stuff into the battle. And of course, cooking and cleaning cookware is, you have to do it right, or you'll get bacteria and the soldiers will get sick, and that's not good. So they were looking for coatings for their cookware, and quasi-crystals were a real possibility, because there's no slip planes or anything. It's really good, hard material. And some company in France was already selling pots and pans with quasi-crystalline coating, so it had to be right. So Laurie Marks hired an undergrad over the summer to do undergrad research. He wanted them to figure out what kind of quasi-crystal coating they had. And they went and ordered some of these pans from France. And the student found out that they just lied. It wasn't a quasi-crystalline coating at all. They just lied.
That's a perfect example of the kinds of things that happen in this class too. And you can get into all sorts of interesting discussions there. Are they intentionally misleading the consumer? Are they just wrong? Is this legal? Is this ethical? It opens up this big probability space to get the students to think about, what are all the potential explanations? What do I believe is most likely and why? And that starts to be real engineering, very different from blocks and slopes.
Right. That's fantastic. So how do you go from teaching them, I presume you teach them how to use a scanning electron microscope, how to do a load frame experiment, those kinds of things. What's the second step? So you said this is the third project.
That's right.
And you talked about the first. What's the second project?
Yeah. So the first project is everybody is lying to you. The second project is, but it is possible to find out the truth. And this is where we get very into characterization. So exactly as you're describing, the students learn to do electron microscopy, optical microscopy, tensile testing, hardness testing, all of these core structural materials characterization techniques. And in this case, I'm also introducing the idea of engineering standards, that there are standard definitions and expectations and sets of properties for pretty much all of the industrial commonly used materials out there. And so students in this case, I do give them a project where a right answer is known and expected, and it becomes a verification exercise, but more so a quality control exercise. We're bringing in the idea of statistics as well and saying, okay, so you've measured that the tensile strength of this standard alloy is 140 MPa. Plus or minus how much? Does that agree or disagree? Is it statistically significantly different from the expected mean value from this alloy? Why do you think that's the case? Is there a cause for these observed differences? Or did you actually find out, no, it's exactly within spec. QA worked. Everything is fine. We're ready to go on and start working with this material. So on the surface, it can appear to be this sort of simplistic, measure the right answer, confirm the right answer, okay, you're done, go home. But once you bring it into this more manufacturing-oriented context of quality control and probability and statistics, there's enough richness there that the students have interesting questions to answer. And my gauge for is it a meaningful question is always, can two different student teams come to two different answers from the same data set and make reasoned arguments about why they're right and the other team is wrong? And the fact that that happens in this project indicates to me that.
That's great. So then the next step is you introduce the computational tools. Now, I know that all of our undergrads for the whole College of Engineering take a course where they learn C++, they learn MATLAB, and the elements of engineering computation, but just the elements. And furthermore, they took that 2 years ago, not even just last year. So what tools do you use and how do you go about introducing them so they can actually use them?
Yes. I've decided to focus on two main computational tools for this course. The first is thermodynamics simulation software. And in this case, we're using ThermoCalc. So the students are using ThermoCalc to first study the phase structure and the sort of expected phase composition of their alloys that they're working with. Again, first a standard alloy, and then eventually they'll get into this design space. And that works really nicely because of the interplay between this course and their thermo course that they're taking at the same time. This is something that, again, the other faculty and I have intentionally interweaved over the years to have students do something in my class that is thermodynamically meaningful. They go to thermo, they learn more detail, they come back to me, they're ready for the next step, and so on. So they're doing these thermodynamic simulations. And the other computational aspect of the course is some finite element modeling so that the students can do FEA on their materials. And in this case, we're doing metal castings in this class, and castings invariably have defects. Students sometimes get the wrong answer, which is not wrong at all. They've done the measurement perfectly well. It's just not what they expected because of some defect in the material. And once the students can be, once I can encourage the students to realize that the answer is different because of some actual physical attribute of the real material system, let's figure out how much effect it had. Is this a good explanation for the observed discrepancies? Then they can use these finite element models to, for example, introduce porosity into a modeled dog bone and say, how much of a stress concentration effect does this porosity have? Or even as something as simple as, there's a funny dent on the surface of my dog bone. Does that matter? I don't know if it matters. I can't do that math in my head. But you know what can do that math? We have a computer sitting right here. Make it do the math for you. You asked a good question, which is the most important part for the human to do in this course. Now let the machine grind out the numbers for you and say, do I need to worry about the effect of this dent?
So I do have to stop you there because you make it sound like, oh, just use the computer and do it. I think it's a little more complicated than that.
It's a little more complicated.
If you told me to go do that, I wouldn't know what to do. So you're using COMSOL, I guess, for your finite element tool? Or using Abacus?
I've used COMSOL in the past. This year, I'm trying out some of the ANSYS products. And every software suite has its own strengths and weaknesses. So
how do you teach them how to use? I mean, it's not at all trivial to use these tools responsibly. It's very easy to use the tool.
Irresponsibly.
But yes. So how do you teach them to use the tools responsibly, to try to simulate something they know in advance what the answer is, to see if they're able to get it? How do you do that?
Yeah. It's tempting to say I don't, but that would be unhelpful. and somewhat dishonest. It is, however, true that there is a senior level course in computational material science that many of our students take, and I do certainly encourage the students to take. So as with any class, there are some places where I say, you know what? We have officially hit the line of beyond the scope of this course. If you want to go learn more, there's a whole class about it. But I do have to get the students to, exactly as you said, a level of using these tools responsibly. So given that it is their first experience, for most of the students, it's their first experience with computational modeling, I really focus on teaching only 2 core fundamentals. The first one is model validation. So that is something that we start with very simple geometries, very simple problems, and having the students do, for example, simulate a tensile test of a dog bone in the software, do a physical test of a dog bone with identical geometry in the lab, compare the results against each other, and start with well-known, accurate data and ask the question, does the model match the experiment? If so, now you start to have some confidence that you can trust that you are using the model correctly and can now go ask more interesting questions about it.
But one of those questions that you already brought up is, what if you have a dent in the material? All of a sudden, you've got to make a new mesh, and you've got to put in that dent, and that becomes difficult to do, I would think. So how do you teach them to approach something like that?
And that's exactly the second fundamental that I do really work hard to get across in this course, is the importance of boundary conditions and numerical approximations. I am not getting into it at an algorithms level of how the computer solves the equations. I'm not an expert in that. We have experts on that. We have courses on that. I'm not going to spend time in the intro lab on implementation of numerical methods. But what I absolutely do ask the students is, how do you set up this differential equation? You've taken differential equations. What does the math look like? And what are the boundary conditions for the problem? And this is an area where I ask and often get the blank look at the beginning of what's a boundary condition, which, regardless of whether they've taken differential equations or not, a lot of these things don't stick the first time. That's fine. That's part of the process. But if I ask it in a very physically situated context of, in the physical tensile test on the load frame, what variables are being held constant, what variables are being controlled by the machine, how do those map onto the different parameters you can control in your simulation? That starts to be a productive conversation. So that's how I approach teaching this idea of boundary conditions, is really asking to students to make the comparison to how the physical experiment works. And it lets me tease out lots of really interesting ideas that the students sometimes haven't thought about of, well, are we controlling the stress or the strain in this experiment? Even something as simple as that can be pretty challenging to get into from an equipment point of view. It requires you to have some sophistication about how the apparatus works. So it leads to all these great conversations about that.
And of course, you can't ever measure stress.
That's
can
right.
only measure strain.
Right.
You must calculate stress from the strain field. When I've come to visit you teaching, you've also done something really interesting, in my opinion, for the way you've set up your laboratory classroom. You threw out all the individual computer stations and replaced them with large screens with several chairs around big screens. Can you talk about that and how you feel that helps the students do? It's a pretty challenging thing to learn all this software.
Yeah, absolutely. The advantage of this approach is that it gets to the students to a place where their default behavior is working in pairs. There's 2 keyboards, there's 2 mice, there's 1 monitor, and a few students do have some prior experience with these tools and get into it pretty naturally, but most of them, again, are starting for the first time. And that buddy system is really valuable, both cognitively and also just emotionally. The fact that they have someone working through this with them who also doesn't know what they're doing, and they can lean on each other for support, both intellectual and just someone to, have a shoulder to cry on occasionally when it breaks for the zillionth time, is a really important part of the course. So that was something that was done really intentionally to de-isolate the students. Computational work can sometimes feel very isolating, especially when you are working on a research problem by yourself. And I really wanted to break that down and say, no, this can be a social learning activity just as much as sitting on the microscope together can be a social learning activity.
Now, normally you have how many people in a team for modules?
Teams are generally 3 to 4 students each. And the way the lab is set up, or rather the way the course schedule is set up, is that I have a few different stations, I'll say, available at any given time. And this way, some of the students will be working on their model. Some of the students will be working on data analysis. Some of the students will be working on image processing from their micrographs. And this is another one of those skills, secondary but also important skill that the course teaches, is just project management and time management. And when you're on a team, why have 4 people sitting around staring at one piece of paper when you could have 2 pairs of people working in parallel and being efficient but still learning quite a lot in the process?
So you really do just have half the team doing the coding together, the other half of the team is doing something else, and then they all rotate positions?
That's often happening. But part of my responsibility in the lab is to know what people are doing. And I'll often catch one of these teachable moments, right? Of, oh, that was a really cool thing. Hold on, I want the rest of the group, team, class, to see this. And so it's also being comfortable owning that space and saying, hey, everyone, stop what you're doing. I'm sure you're having fun with something else, but this is worth everyone seeing all together. And it's also very validating then for the students who caused that to happen. They're like, oh, I did something that's so interesting that the teacher wants the whole class to learn about it. That can be a really powerful experience.
That's awesome. Now, maybe you can talk a little bit about the kinds of alloys they're designing and how you actually make them.
Yeah, there's always logistics as one of the biggest problems in the lab course, is just how do you physically do the thing? So I have students working on aluminum alloys in this course. There's several reasons for that. One is safety. Aluminum has a fairly low melting temperature, so it reduces some of the safety challenges in the course. Another is just its ubiquity as a very practical, everyday industrial material that students are surrounded by all the time. But also pedagogically, there was an important reason that I chose aluminum, which is that the microstructures are fairly tractable for beginners. A student can look at an aluminum silicon alloy, see 2 or 3 phases, and not be overwhelmed, and feel that it is a problem that they're actually able to work out. And as we get into this design problem of the students creating a novel alloy, then one factor that I always encourage the students very strongly to consider is, I know you want to throw in like 8 elements because the periodic table is very exciting and interesting, but the harder you make it for yourself, the harder it's going to be. And I'm not talking about material hardness, I'm talking about difficulty here. And sometimes they listen, sometimes they don't. But that's also the hallmark of a good design experience, is sometimes they ignore my advice and, they learn from that experience as much as anything else.
Design their material with whatever additives and other alloying elements they're going to put in. Do you then get a shopping list and you have to go out and find all these things? And I presume it's either in nugget form or powder form. What is, like, what if they want to put calcium in? How do you do that?
Nobody's asked the calcium question yet, so I hope that never comes up. But it takes about a month of pre-work, both for me and for the students and for the lab staff, all of us really working together to make this happen. So it starts out first, as in my opinion, any good design project should, with an actual purpose. It's not make this for the hell of it to see what happens. It's choose an application in the real world, something where aluminum is used, where you say, what are the relevant properties for this application? Why is it important and meaningful in the world? And how could the existing alloys be improved to make the performance of the material better in this context? So students spend a week identifying that problem definition first. Then I have them get into the literature, see what solutions are out there, learn the effects of different alloying elements, but also go back to modeling as well. ThermoCalc, at this point, they have some experience with it for phase structure analysis, but now I have them start using the property predictors in ThermoCalc, which are often wildly inaccurate because the students don't know what they're doing, and that's okay. That's part of the experience, but at least gets the students being intentional about exploring the space of options and saying, if I increase or decrease the amount of this or that constituent, how do I expect my properties to change? And if I can get them thinking about those trends, even if the numbers aren't quantitatively accurate, they can at least make good informed decisions about the chemistry and the thermal processing of their alloys that they're designing. So that takes a week. So they've defined the problem, they've done the modeling, and then they end up with their candidate design. They send that to me, put together a shopping list, buy things, get things delivered, and then the students do the manufacturing. That takes a week. So melt, pour, make dog bones, do the characterization, and they spend the last few weeks of the semester completely characterizing this novel alloy that they've created and ultimately answering the question, did it do what I wanted it to do? Why or why not? And that's what the final presentations for the class are on, is answering that question.
Do you end up needing to use the induction furnace, or can you do this just in a box furnace?
This could be implemented at a few different levels depending on the facilities that are available. So on the upper end, for our dear listeners out there, if your school has a foundry, take advantage of the school foundry. You can do so many interesting things in that environment. And in our case, we have one single casting furnace, so we don't have a big foundry set up, but we're melting 30, 40 pounds of aluminum at a time, and the students are processing that to make their dog bones, to produce their specimens. But on a smaller scale, you could absolutely do something similar with just a couple of box furnaces, some 10-pound crucibles, a small dog bone mold. It wouldn't take a huge facility to implement this same sort of course design and course structure at really any university.
That's great. And do you have any examples of the reports? I don't know if that's, you'd probably have to get the students' permission before we posted anything, but we could certainly put up some resources if you were interested.
Sure. Yeah, without naming the innocent, the products that the students come up with at the end of the semester are so impressive in the quality, the thoroughness of their analysis, also the honesty is something that I think is another good indicator of a good design experience, is that students really are willing to come out and say, you know what, this didn't work out the way we wanted to, but here's why it didn't work out the way we wanted it to. Here's what we could do differently next time. Here's all the things that I learned by going through this experience. And they really come out and just talk about these things in their presentations and their reports. And so it's very evident that even though each student learns something different from this course, everyone is saying, I had an experience here that really changed the way I think about doing materials science.
That's great. Now, how long have you been teaching with this module?
So I started the design project 5 years ago. I think I'm almost doing it right now. Maybe in another 5 years, I'll be all the way there. And as with many things in the world, this evolved from prior work that we were doing and different metal casting projects, different characterization projects. But as I said earlier in the show, it was me listening to the seniors and hearing from the seniors, what do you wish you had learned last year that you didn't get, that really made me say, we need a design experience in the junior year.
That's great. So do you have any anecdotal, have you ever talked to alums of your course who might have taken the senior design course and told you that your course was valuable, or people who've gone out to industry you've seen later? Do you have any anecdotal stories you can tell us?
Sure. I can think of several students who had really meaningful career experiences that followed from their experience in this course. So one of our students last year ended up landing a summer internship at Caterpillar because of their experience with metal casting in this course. Caterpillar was looking for someone to work on ferrous alloys for farm equipment of all things, but that's a really important real-world engineering problem. And so the student was able to walk in and say, yeah, so I have alloy design experience and I've been pouring metal in my classes, and one thing led to another, summer gig attained. But even after they graduate, when students are applying for their first sort of real jobs, there was a student 3 years ago who ended up at US Steel, same sort of story. They really enjoyed this experience in the class, but more so realized how important the chemistry of alloys is to their properties, and this particular semester, how sensitive small fluctuations in chemistry can, or how sensitive the alloy can be to small fluctuations in the chemistry. And that was something that this student spun into, a good job interview story to say, yeah, I had this experience where it turned out that the amount of copper in my alloy was off by 0.5% and everything went wrong. And it was, I guess, something that the recruiters were very happy to hear about.
Now, I also know that you happen to be the faculty person for the American, I guess they just call themselves AFS now. Is that right? Well, because what it used to mean is a little sexist.
Yeah, I'm not sure if it's like KFC where it doesn't mean anything anymore, but yeah, it is now the American Foundry Society.
Okay. And has that and the connections you've made with that community helped you at all with what you're doing?
Oh, absolutely. I have learned so much from my colleagues in AFS, and it has been a very helpful experience to just go to people and say, I'm having this problem. What would you recommend? Or to to say, I have this idea. Is this even going to work at all? And they'll say, well, no, but here's why. Or even worse, they'll say, it seems like it's worth trying, which sets off the alarm bells of, okay, this is going to go wrong, but they need me to experience why it's going to go wrong so I can learn it for myself, which is also the hallmark of good teaching, right? So yeah, there's a lot of people in the AFS world who are very happy to see students doing more of this and who are happy to work with faculty and with peers to enable students to have these experiences. So this is absolutely something I could not have figured out or done by myself. It's taken a lot of support and guidance from people who came before me who actually know what they're doing to help fill me into the point where I could execute.
That's great. So if a materials program department came to you and said, we'd like to start some kind of casting activity in our labs, what advice would you give them?
My advice would be, come talk to me for a week in the summer and we can go through the whole thing together. And hey, if anyone's out there, that's a genuine offer. I would love to talk about this course with people out there, and it could be ported wholesale. It could be steal little bits of ideas that you think might be useful or important to your own students. So just starting by having that conversation and doing some of that planning and thinking about what's possible, how could I fit this into what I'm doing now, is always a great start. The other angle that I'd recommend is, if it's a similar context of maybe this is like a sophomore or a junior lab course, then just as I did, talk to the people teaching the seniors and say, what do our seniors need that they're not getting yet? And then talk to the seniors and say, what do you feel like you're missing that you're not getting? And if you can tie some of those into your course design and how you get your students having design experiences earlier in their academic careers, then I think it's going to be a lot more productive for everyone.
That's fantastic. Well, we've already talked 35 minutes. So I think with that, we should probably say goodbye. And thank you very much for sharing all that, Tim. And your offer is quite generous. So hopefully some people will take you up on it. And of course, since we're hosting the North American Materials Education Symposium here in Ann Arbor, anyone who comes to Ann Arbor is going to get to talk to Tim. So we hope everybody comes. We'll be putting the links to submit papers or to register. It's going to be fairly inexpensive. So that's going to be, I think, around August 7th, 8th, something like that, on a Wednesday and Thursday.
Early August, yeah.
And then ANSYS is going to run some workshops on Friday. So it's looking like a good time, but I'm sure during that time you'll be able to offer some lab tours and help anybody who might want to develop these kinds of things.
Absolutely.
So thank you very much. Thank you for listening, and we'll see you next time.
Thank you. See you next time.